Okay, we are back for special topics of semiconductor technology. Next, we'll discuss the second part of chapter 3. We'll discuss about what is N-type semiconductor, what is P-type semiconductor, and what is the conductivity or resistivity based upon the dopant concentrations. Okay, this slide shows you the crystal structure of a single crystal silicon. To be a semiconductor, it has to be single crystal. If it is not a single crystal, it is not a semiconductor. Before to discuss what is so-called N-type and P-type semiconductor, let's look at the atomic structure of a single crystal silicon. This is a very simple structure of unit cell of single crystal silicon. It's basically a so-called face-centered cubic, the so-called FCC structure. FCC structure is a very common atomic structure for crystal. It's basically a cubic materials with electron occupied at the corner, totally 8 corners. The 6 face for the cube. Basically, at each of the center of the cube, the face, you got 1 extra atoms. So this is the structure. It's a face-centered cubic. The material like aluminum, gold, copper, and silver. These materials has a face-centered cubic structure. It's a very common structure of the single crystal. And for silicon single crystal, it's a variant based upon the face-centered cubic structure. Let's look at over here. If we cut this cube into 8 different small cube. Okay. This is 1/8 of the structure. So you got 3. Let me see. These 3 are face-centered. Okay, these are 3 face-centered atoms, and you got another extra atoms at the corner here. So based upon this, you can come up with a structure like this. Okay, you can come up with a structure like something like this. It's a tetragonal. within the tetragonal, the body center, at the center of the tetragonal, you got one extra atoms. You got one extra atom at the center. And this tetragonal structure is basically the crystal structure of silicon. So that means from the center point atom point of view, you have 3 phase center atom and 1 corner atom form a structure. So put it in a simple geometry, that would be 1 atoms and then the other 4 atoms. Okay, this would be something like that. And this is a basic structure of atomic structure of the silicon wafer. So come back to here. You have 1, 2, 3 face centered. One, 2, 3 face center atom, and then you got corner atom, and then you have the atom at the center of tetragonal. So put it in a simple structure, this will be the 4 atoms. 1, 2, 3, 4, with the center atom here. Since the silicon is in the periodical table with group 4 is a group 4 element. That means at the outermost S and P electron shell, it total occupy with 4 electrons. So each of the silicon atom is supposed to have 4 electrons. Let's see here. This one, this one, this one, and this one. For the silicon atom at the center here, it has 4, the red one, electron occupy the outermost SMP electron shell by itself. For a compound materials, in general, it will form a bonding between atoms to form a structure similar to the inert gas. Let's come up to here. Come back to here. Look at the inert gas. Over here, the inert gas. The so-called inert gas is the most stable element, most stable electron configuration. So you either have 2 electrons, or 10 electrons, or 18 electrons to become an inert gas structure. So all the elements here try to become inert gas structure one way or the other. For example, silicon. Silicon here has 14 electrons. To become an inert gas, either you lose 4 electrons to 10, become neon electron, or you got extra 4 electrons, become 18 electrons to form an argon atomic structure. So for silicon, either drop 4 electrons or capture another 4 electrons to form neon or argon structure, and it becomes a stable atomic configuration. So coming back to the silicon configuration. So the silicon in the outermost electron shell has only 4 electrons. So by combining, forming a bonding between the 4 face, center, and the corner atom, you have 1, 2, 3, 4 atoms form a covalent bonding with these neighborhood electron atoms. They share electron to each other. For example, the first electron on top of the center silicon atom. This electron has 4 outermost shell electrons, and then it will share the electron with center silicon atom. So this electron being shared with center atom, and the red electron shared by the blue atoms. In the similar manner, this electron, the red electron, is shared by the number 2 atom, and from number 2 atom, 1 electron share with this center atom. Similarly, number 3 atom, number 4 atom. Those electrons are shared with neighborhood electron. No loss and gain. Simply share and form a so-called covalent bonding. In that case, when the center silicon atom form covalent bonding with 4 extra atoms, then it will form a similar atomic structure similar to argon. It has 18 electrons. So for silicon, it has 14. Silicon has 14 plus another 4 share electron equal to 18. So it will form a similar structure as argon. So it becomes stable. And this is how silicon form a single crystal structure. After the center atom form a stable configurations, and all the other silicon forming a bonding in the neighborhood atom in the same manner, so form a solid. This is a single crystal silicon crystal structure. So now you have the idea. Silicon has 14 electrons. It will capture or share another 4 with the other 4 electrons, and to form a stable configuration. Okay, then next let's talk about why we use silicon as the semiconductor substrate. As we mentioned, the first single crystal material used for IC fabrication is germanium. Okay, germanium. And 2 years later, silicon single crystal is used to creating the integrated circuit. And right now, more than 90% of the industry was dominated by silicon used as a substrate for IC fabrications. And what's the reason why we use silicon instead of germanium? For the silicon, it's abundant and inexpensive. Silicon ore. Silicon is one of the highest element content in the Earth's crust. So it's abundant. So it's cheap, inexpensive. Second, we'll talk about the thermal stability. Because of silicon, it's easy to form silicon dioxide. Silicon dioxide has about energy gap. Silicon dioxide energy gap is somewhere around 8 electron volt. We use a lot of silicon dioxide in IC fabrication. Okay, it's a very strong dielectric materials and relatively easy to form. Okay, and with very good insulating properties. So the larger the energy band gap can operate the IC at a larger temperature range. And silicon has the melting point somewhere around 100 and 1500 degree, somewhere around that. So it is stable at elevated temperature. Other than the strong dielectric and easy to form for the silicon dioxide, the silicon dioxide can also be used as so-called diffusion doping mask. Okay, in the future we'll discuss about the application of silicon dioxide. You have a lot of function using silicon dioxide at different location, different occasions, and also it will come with different name, something like native oxide, sacrificial oxide, screen oxide. So it has a lot of application, and we'll discuss that in the future. So this is the reason why we use silicon as the substrate for the materials. Okay, next we'll discuss what is the N-type semiconductor and what is N-type dopant. As we mentioned, for silicon, it is combined with the silicon need to have a covalent bonding between 4 electrons from outermost electron shell. From here, let's see. You have center electron here. Okay, your center electron here. Let me see. Being replaced by arsenic atoms. And remember that arsenic has 5 electrons. So it will come up with 1 extra electron here. Okay, I think my cursor somehow a little bit function not well. Okay, then let's conclude the first section here. Then we'll come back with the next topic of N-type P-type semiconductor. Okay, later. Okay, then let me fix my pointer. Okay, I'll see you next time.